So, the most popular approach to inferencing, uh, let's say, all structured prediction and all graphical models, factor graphs, and so on, is the sum product algorithm, a simple variant of belief propagation. And we shall now make use of factor graph framework to derive a powerful class for efficient, exact inference algorithms that are applicable to tree-structured graphs. Here we shall focus on the problem of evaluating local marginals over nodes or subsets of nodes, which will lead us to the sum product algorithm. So there is an algorithm, as I said, Judell-Pearl, 1988. I've explained his beautiful ideas on causality exactly 2 years ago. And he has written at least two great books. One of them is the book of Why, if you like philosophy, and the other one is about graphical Bayesian networks and those things, and causality, and counterfactual, and those things. So it's very old idea, and it goes back to 1988 by great people like Judell-Pearl. And now we are talking about the same thing, but now we call it sum product. It's very similar. And we first convert the original graph into factor graph so that we can deal with both directed and undirected models. So our goal is to exploit the structure of the graph to achieve two things: to obtain an efficient, exact inference algorithm for finding marginals in situations where several marginals are required to allow computers to be shared efficiently. So the sum product will sum over all x except the one that you're marginalizing at. So we see that the joint distribution can be written as a product of the form of this, and this is just the neighbors of x. So S is inside the neighbors of S, and you know what I mean as you have watched my previous video. And graphically you will see that this is the meaning of this. You're passing a message from this f of s, this factor node, to the normal simple node x. For example, in NLP you have attributes, and you're passing them in order to understand what is the label of that, what is the relation of that to the other nodes that, for example, you have. And they're passing the message from this factor node to x. And here, so these are messages going from s to x over all s that are neighbors of x. And here is the opposite. Now we are going from simple nodes to factors, because there are two possibilities. You either go from simple node to factor node, you're passing messages from that, or you're passing message from a factor node, like previous picture, your factor node to that simple node. So in this case, we call it G, and we sum over xm, but we multiply over all the things, all of these factors that happen. So G1, G2, Gm. And so this is the message that goes from f of s to x. So we have two distinct kind of messages. Those that go from factor nodes to variable nodes, like this, factor nodes to variable nodes, and those that go from variable nodes to factor nodes, like this. In each case, we see that messages passed along a link are always a function of the variable associated with the variable node that link connects to. And finally, we derive an expression for evaluating the messages from variable nodes to factor nodes, again by making use of subgraph factorization. And if you combine them, you will see that it's just a multiplication of those messages. And of course, it is, if you want to have a good numerical algorithm, always go to the log space. Then you don't have the problems, many problems. And of course, at each step you should do, I will show that you should do normalization, otherwise it gets divergent. So here, first we see that if a leaf node is a variable node, then the messages that it sends along its one and only length is given by, we put 1 to that. Similarly, if the leaf node is a factor node, we see that the message sent should take this form. So any variable we consider as a root, and then we know how to say which one is priority, which one is parent to the other one. So we always, if you fix one of them, then you know what are the rest of them. You know the hierarchy of that, and you go from the leaves to the once you go from leaves to the parent, and then from the parent to the leaves. So the probability of X is the factor itself times the messages that goes to that factor. For example, if we know that the unnormalized joint distribution is just FA of x1, x2, this one, multiplied by FB of x2 and x3, multiplied by this, multiplied by FC of x2 and x4. If you multiply them, then this is the probability of X. So in the sum product, as I said, because x1 is a leaf, so we put 1. Because x4 is a leaf, we put 1. Because and that's it. These are the leaves. And now we go to factors. Because now FA is the factor between x1 and x2. We sum over x1. We are passing the message from FA to x2. So this one is just a summation over x1, because x1 could be different things. One label 2x2, another label of that 2x2, another label. If you sum over all of them, you get the message that goes from FA to x2. So we are considering all the labels because we are summing over all the labels. It's just one number, but we have considered this as well. And the next thing that we should think about is mu of x2 to FB. x2 to FB. So this one is just mu of FA going from FA to x2 times mu of FC goes to x2. And so this is, you see, everything is very intuitive. And so first we go from leaf nodes x1 and x4 to our root x3. So this is the root. And first we go here and then we go here. And And then we go the opposite way. So this is still the root, but now we go to the other direction. And after a while, it converges. You will see that the messages don't change anymore. Just the residuals. If you have seen the partial differential equations, in, for example, Navier-Stokes equations, you want to solve it numerically, you go from the boundary layers, you have the value on the boundary. For example, here our boundaries are observed things. For example, the words of a sentence, we have observed them. And then this is a partial differential equations, and then gradually from the wall you go to the inner domain and calculate all the nodes. You repeat this until you have everything is converged, and these values don't change anymore, not too much. And so you can think about it like that. It's a good metaphor. Partial differential equations for me is a good metaphor when I think about these things, because all of them are physics. You either work with partial differential equation, Navier-Stokes, Maxwell, and electrical engineering, those things, or you're using it inside your brain. It's like this. You have a factor graph, you pass the messages. And as I said, in the opposite way, you will go from root to the leaves, then you have the similar messages. So we can verify that this marginal P of x2 is given by the correct expression. And Professor Yuri Leskovec in Stanford, he teaches these things very beautifully. So you see that here he's saying that you multiply all the messages that goes from K to I. And because K could be all the neighbors, for example, U to I, V to I. So if you multiply them, then we have what is the probability of your label, because this itself has a label. What is the probability? What is the potential of that? We can think about as a prior in the Bayesian framework. And what is the sign of yi and yj? Because now we have collected everything. You want to pass it to the j. So this is the sign of, so it's binary, yi, yj. This is unary, just one variable. It needs just one variable. Now here it needs two variables, because we need we need to know how good is that if we have a label yi here, then it is connected to a node that has label yj. How good it is. So we are maximizing this probability. And the message is just a multiplication of these three terms. So the message that goes from I to j is this. So his slides are very beautiful. But I'm very lazy. You see, my slides are just text, and it's not good. And another great researcher is David McAllister. And you see, he is teaching about loopy belief propagation here. He's saying that you should normalize things here. Otherwise, it diverges, because if you don't multiply, it becomes bigger and bigger. It amplifies everything. But if you just normalize this, then it's because you are multiplying something that is less than 1, there are probabilities, so it will not diverge. And it becomes even smaller. And here he's talking about how can we calculate the probability of each node. And he's the same person that I've explained his article on Pack Bayesian theorems in 1998. If you remember my playlist for deep learning in 2032, I explained Pack-Bayesian framework and his article in 1998 and 2000 are very fundamental for Pack-Bayesian learning.